Hello, this is Mrs. Edwards, and we are going to work through the review and preview problems in the CCG book, numbers 817 to 823. 817 says, on graph paper, graph triangle ABC if point A is at the ordered pair 3, 0, point B is at the ordered pair 2, 7, and point C is at the ordered pair 6, 4. What is the most specific name for this triangle? Prove your answer is correct using both slope and side length. So when we take a look at the slope, to go from point B to point C, if you draw a slope triangle, we go down. Notice that we're counting by 2. So we go down 3 over 4. So for line BC, our slope is equal to down 3 over 4. When we look at line AC, if we go from point A, remember we always read from left to the right, I notice I run 3 and I rise 4. So my rise over my run is 4 over 3. I notice that my slope for line segment CA, 4 over 3, is the opposite reciprocal for line segment CA, which tells us these are opposite reciprocals, so we have perpendicular lines which form a right angle. I then want to look at the length of my sides. So using my triangles, my triangle for CA, if I use my Pythagorean theorem, and my 3 and my 4, 3 squared is 9, 4 squared is 16, 16 plus 9 equals 25, which tells me that my hypotenuse is 5, or the length from A to C is 5 units. I can also take a look at the length of B to C by also using my right triangle. 3 squared is 9, 4 squared is 16, 16 plus 9 is 25, and the square root tells me that the length of BC is also 5 units. So if my sides are congruent, 5 units and 5 units, my slopes are perpendicular to form a right angle, I have an isosceles right triangle. It then asks us to find the measure of angle A. So we can find the angle of measure A in a variety of different ways. We know that both of our sides are 5. We know that this angle right here is a right angle because we have perpendicular lines, which then tells us because our sides are congruent, our angles must be congruent. We know that our angles of a triangle add to 180 degrees. So if we subtract our 90 degrees out, we have 90 degrees left. We need to divide it by 2 because it's an isosceles triangle. So the measure of angle A, and actually the measure of angle B, is equal to 45 degrees. 8-18, the exterior angles of a quadrilateral are labeled A, B, C, and D in the diagram below. It wants us to find the measures of A, B, C, and D, and then find the sum of all the exterior angles. So I know that my straight lines equal 180 degrees. So if I take 180, because it's my straight angle, and subtract 93 from it, 93 degrees, I know that angle A is equal to 87 degrees. I then, when I look at angle B, know I have a straight angle. So if I take 180 minus 97 degrees, it's going to give me angle B, which is 83 degrees. When I take a look at angle C, again, I take 180 and subtract 84 from that because it's a straight angle, which tells me angle C is 96 degrees. And then my final angle, angle D, I know that in a quadrilateral, everything in the inside adds up to 360 degrees. So if I subtract 84, so 360 minus 84 minus 97 minus 93, I get 86 degrees as my interior angle right here. This is a straight angle, so I'm going to take my 180 and subtract my 86, which will give me angle D, and angle D is 94 degrees. It then asked me to find the sum of all my exterior angles. So when I take A and add it to B, add it to C, and add it to D, I notice that my exterior angles add up to 360 degrees. 8-19 says find the area and the perimeter of the shape below. When we find area of a shape, we are looking for the unit squared and everything inside. When we find the perimeter of a shape, we are looking for all of the outsides added up. So the sum of all these sides. So the first thing we need to do is we need to make sure that we have all of the side lengths in order to find the sum. So notice our shape is this piece right here. So we are going to have to use our Pythagorean theorem to find a few of our missing pieces. So for this side right here, because we have a right triangle, if we do 3 squared plus 6 squared, it's going to equal our hypotenuse squared. So 9 plus 36 is equal to 45. And the inverse of squaring something is square rooting it. So when we take the square root of 45, we get C is approximately 6.7. So we can label that side we just found as 6.7. We then can find the other side of this little triangle using the Pythagorean theorem. 3 squared plus 3 squared, 9 plus 9 equals 18, equals C squared. Inverse of squaring something is square rooting it, so when we take the square root of 18, we get approximately C is equal to 4.24. So we can go ahead and label that 4.24. And then we have one other piece to find, which is this piece right here. So when we are finding this pink triangle, if you notice the length of this entire side right here is 6 plus 3, which is 9, which would make this 6. We then have a length of 5. So we can say this length is 5, which would make this side of our triangle 3. So we can use the Pythagorean theorem, 3 squared plus 6 squared equals c squared. So we know that c is approximately 6.7. We then can make some observations, and I noticed that this purple triangle is the exact same as this pink triangle that we just found here. They are congruent because both of their legs are 3 and 6, and their hypotenuse are 6.7. So when we're finding the area, those essentially cancel one another out if we move this pink triangle to where this purple triangle is, and then we could be looking at a rectangle. So if we're looking at this rectangle, in order to find the area, remember, of a rectangle, we do base times height. So the area of the rectangle equals 9 times 5, which gives us 45 units squared. Okay, but we have to subtract out this blue piece right here. So to find the area of a triangle, it's 1/2 base times height. So we're going to subtract, our base is 3, our height is 3. So 1/2 of 9 is 4.5. So if we subtract 4.5 units squared from 45, we get 40.5. Our area of our shape is 40.5 miles squared. So 45.5 square miles. We then do need to look at the perimeter of our shape. So perimeter, we are going to take all of the sides and add them up. So our perimeter, we have 6.7 plus 2 plus 3 plus 6.7 plus 5 is this side right here, plus 4.24, which gives us a perimeter of about 27.7 miles. So in 8-20, Crystal is amazed. She graphed triangle ABC using the points 5, -1, 3, -7, and 6, -2. She then rotated 90 degrees counterclockwise, so you can see in our picture, when we rotate counterclockwise, our original triangle moves up into quadrant 1. Meanwhile, her teammate took a different triangle, TUV, and rotated it clockwise about the origin to find T prime, U prime, V prime. Amazingly, ABC prime and TUV prime ended up using exactly the same points. Name the vertices of triangle TUV. So looking at this red triangle, it's triangle A prime, B prime, C prime. Looking at the blue triangle was ABC. Looking at this next in the green triangle, if we take TUV and we rotated that one to get T prime, U prime, V prime, if we end up, they end up being directly on top of one another. If we rotate this one into this quadrant, you can see our original, if we rotate this blue up and the green over, they would form the exact same triangle, and the coordinates of that triangle would be -5. So looking at this new triangle we created, our coordinates, our ordered pairs, would be -5, 1, -6, 2, and -3, 7. (8-21) says write an equation for each of the following sequences. So it's really important that when we write an equation for a sequence, that we take into consideration that they only give us our first term. We also need to determine whether it is arithmetic, based upon adding or subtracting to get to the next term, or geometric, which is multiplying to go from one term to the next. So when you look at your pattern, it has to do the same thing every time. So to go from -30 to -15, I'm I'm adding 15. To go from -15 to 0, I'm also adding 15. So I know that it's arithmetic, which means it's going to be similar to a linear equation. So when I write an equation for a sequence, I'm going to use a sub n. I know that it's changing by 15 each time, so 15 times n, but then I need to find my 0 term. So the inverse of adding 15 would be subtracting 15 to go this direction, which would give me -45. So we put -45 as our 0 term, and we just wrote an equation for our sequence. Looking at letter B, to go from 9 to 3, my first instinct is that it divides by 3, and 3 divided by 3 is equal to 1. However, when I'm writing a geometric sequence, it has to be written as using a multiplier. So dividing by 3 is the exact same thing as multiplying by 1/3. So this sequence is geometric, which is similar to an exponential equation. We still used a sub n as our notation. We need to find our 0 term, which in this case would be 27, and we do that using the opposite, so it would have been multiplying by 3. So my initial term is 27. My multiplier is 1/3, and I raise it to the nth power. 8-22, Suzette started to set up a proof to show that if line segment BC is parallel to line segment EF, so BC is parallel to EF, AB is parallel to DE, and AF is equal to DC. Then line segment BC is congruent to line segment EF. So my reason number 1 would be all of that information is given to me. Then my second statement says the measure of angle BCF is equal to the measure of angle EFC. So BCF is equal to the measure of angle EFC. and EDF is equal to BAC. So I know that those angles are in fact congruent because they are alternate interior angles. So alternate interior angles of two parallel lines cut by a transversal. So because these lines are parallel, to one another, and line segment AD cuts through all of them, we have alternate interior angles. I then can state that line segment FC is equal to line segment FC because of the reflexive property. It's a shared side. AF plus FC, so AF plus FC is equal to FC plus CD, and that is what we call the additive property of equality. Adding the same amount to both sides of an equation keeps the equation true. Statement number 5 says AC is equal to DF. And we know that AC is equal to DF because of segment addition, so it just takes it a step further and writes those as individual segments. We then know that triangle ABC is congruent to triangle DEF based upon the angle-side-angle congruency theorem. If we know that two triangles are congruent, you can see our reason number 7 is if we have congruent triangles, it means that our parts are the same. So we can in fact prove that BC is congruent to line segment EF. 8-23 is a multiple choice question, which you could see on the ACT. Which equation below is not a correct statement based on the information in the diagram? 3x plus y is equal to 180 degrees. This is in fact true. So 3x plus y absolutely is equal to 180 degrees because these lines are parallel. So those would be same side interior angles. B says 2x minus 1 is equal to 4 minus x. Well, I do not think that these are equal to each other. I think that if you add them, they're equal to 180. So I think B could be incorrect. 2x minus 1 is equal to 5y minus 10, These two angles are absolutely equal because they are alternate interior angles. We have parallel lines cut by a transversal. 2x minus 1 plus 3x is equal to 180 degrees. These two angles right here are same side interior angles. And when we add same side interior angles, they equal 180 degrees. So the only answer that is not correct is B.